Am I audible? Patita Pavan, Prachi, Maneshwar. Anyway, welcome to our block 3, that is quantum ensemble theory class. Now we have 4 units to be discussed in this class: fundamentals of quantum statistics, quantum statistical ensemble, Bose-Einstein and Fermi-Dirac statistics, applications of Bose statistics. So the first one is the first discussion to be done in this chapter. I will focus on unit 8, that is fundamental quantum statistics. What is different between classical and quantum statistics? Postulates of quantum statistics, microstates in quantum systems, microstates in density matrix. So the first thing is how we can distinguish between the particles. In Maxwell-Boltzmann statistics is true for distinguishable particles, but the quantum statistics is true for indistinguishable particles. So what are identical particles? Many systems in the nature are made up of several particles. These particles have same mass, charge and spin. For example, the electrons in an atom are identical particles. The identical particles are defined as those particles which cannot be distinguished from other. The other way of distinguishing particles is by track of the trajectory. But in quantum mechanics, the concept of trajectory does not arise. So we define the position of particle and state of the particle by means of a wave function. Hence, wave function in quantum statistics plays a vital role in explaining the quantum ensemble theory. In this case, we distinguish the identical particles in by 2 ways. The wave functions may be symmetric if they have symmetric spin, or 2 identical particles described by a wave function which are symmetric, and exchange of particles. If identical particles have 0 spin, then they are symmetric particles. If identical particles have not integral spin, that is spins having half or 1 by 2, 3 by 2 or 5 by 2, they are treated as the particles having antisymmetric spin. Hence, the identical particles may be spinless particles, or identical particles may be spin half particles. So depending on that, the quantum statistics is needed. Then why quantum statistics came and why quantum ensemble theory came into picture? The reason is, when Maxwell-Boltzmann statistics was taken into consideration, the phenomenon like conduction of electron in metals and photons in black body radiation was not explained. Photons in black body radiation was not explained, as a result of which the quantum statistical ensemble came into picture to explain when the photons arise in case of black body radiation, the classical statistics fails. So quantum statistics deals with the indistinguishable particles. Classical statistics deals with the distinguishable particles. When the occupation index is comparable or greater than 1, then we say the particles are indistinguishable. All the natural systems obey the principle of uncertainty. So the system in the nature of quantum statistics obeys the classical statistics, and classical statistics is a limiting case. So quantum statistics was first given in 1924 by Bose, who suggested bosons are the carriers of those state of particles. But later on, in 1926, Fermi-Dirac statistics came into picture. We will discuss them. But here, we will come across one thing, that what is our difference between classical and quantum statistics. What is basic difference between classical statistics and quantum statistics? We will go through it. What is basic difference? You can see these two graphs. These bars in this graph are state and solid circles are particles. The bars are state of particles, and the solid circles represented here are your particles. So if you compare these two figures, we start from these two figures. The first figure represents a classical picture of bars and solid circles, and the second one represents a quantum picture. This is a quantum picture. This is a classical picture. So these two, you can clear that how the classical picture and quantum picture varies. Why it happens? Because the photons in a cavity of electrons of an atom cannot be distinguished. So they are indistinguishable, and we cannot distinguish between electronic configurations of in p orbit or m orbit or q orbit or n orbit. This is because of indistinguishable nature of particles. So quantum statistics arises mainly due to indistinguishable pictures. Then what are the postulates of quantum statistics? First postulate, remember, first postulate, you can also note the state of a quantum mechanical system which includes all information must be represented by a normalized gate. If psi is a wave function, then the normalized gate mod psi written by this form is called normalized gate. So the state of a quantum system or quantum mechanical system which includes all information is represented by a wave function psi or gate psi. The second one is any physical observable quantities like position, momentum, energy can be represented mathematically by an operator, say A with a subscript OP, which acts as gates. So AOP acts as gates. Now third postulate is the only possible result of a measurement of an observable is one of the eigenvalues AN of the corresponding operator AOP. Remember, find this equation. AOP is a operator, psi is a normalized gate. So the quantum mechanical system, when the operator AOP acts on psi, this is an eigenvalue equation corresponding to eigen operator is gate psi, eigenvalue function is gate psi, eigenvalue operator is AOP, and eigenvalue is AN, generates the same gate. That's why we present this, because it represents an eigenstate of matter. So considering this, we move forward to explain the quantum statistical phenomena. Suppose we will consider a plane as an example, a plane polarized light, uh, and the plane of polarization is parallel to the crystal axis of a tourmaline crystal. When the light passes through the crystal, it will pass through the axis, it passes through the crystal, but if it passes perpendicular to the plane of polarization, then no light will pass. So we consider plane polarized light as an eigenkate. In this case, examples mod psi, ket psi is a polarized light representation. And the parallel perpendicular orientation of the tourmaline crystal is denoted by operator. We represent this operator either T parallel or T perpendicular. So above situation indicates that in quantum statistics, we have eigenvalue equations. How those equations are represented? They are either T parallel acting on psi measures this, gives a value, eigenvalue 1 and generates the same ket. Similarly, T perpendicular acting on psi measures it, this is the eigenvalue and generates the same wave function. Now, these two operators, T parallel and T perpendicular, can be expressed, the linear combination of those two operators, T parallel and T perpendicular, can be written as T parallel component cos T parallel cos theta plus T perpendicular sin theta. And we tell this is equal to T operator. As we considered A operator, in case of polarization of light as a specific example, we take as T operator. So what is the fourth postulate of quantum statistics? Fourth postulate is, we know statistical mechanics is dependent on probability. When you consider eigenvalue equation, the probability of obtaining the eigenvalue An in a measurement of observable AOP on the system in the state psi is given by PAN is AN psi. This is ket, this one is brass, so this is mod psi square. As you know, AN acting on psi, so probability of finding this, and AN is a normalized eigenket corresponding to operator AOP. So we can interpret this probability with the normalized eigenket AN, and by Malu's law, we know from polarization that I0 cos square theta by I0 is cos square theta or cos theta whole square, which is the square of your coefficients T parallel or in T operator. So this is the fourth postulate, which suggests that in quantum statistical mechanics, when we calculate the probability, what we calculate? We take the probability of the eigenvalue An, which is measured by an observable AOP. In the same thing, another postulate of quantum statistics is, after measurement of an operator, it gives a eigenvalue An. So the quantum system in a new state is a normalized projection of the original ket or kets corresponding to the result of measurement. That means we can, the resultant ket psi dash, psi is the initial ket and Pn is the probability acting on this ket divided by square root of psi Pn psi. This is a normalized factor. So after measurement of operator A, we obtain a result, and corresponding result of measurement is represented by this equation, that is psi dash, that is the resultant K, is the probability of this one divided by your normalized factor. The sixth, the postulate is the time evolution of a system. Remember, in statistical mechanics also, classical mechanics, the time evolution is governed by the Hamiltonian or total energy operator. That means it obeys Schrodinger's wave equation. What is Schrodinger's wave equation? IH cross d by dt ket psi t is equal to ht psi t or et psi t. IH cross d by dt psi t is ht psi t. Now, these are, while considering these postulates, we must know these postulates are required to give an idea or to describe the state of a quantum mechanical system, and which leads to the role of, which examines the role of uncertainty principle and specifies the state using Schrodinger's time independent equation. So we have two things to be discussed in the light of these postulates. First one is contest of uncertainty principle. What is uncertainty principle? That is, you know the uncertainty principle, delta x into delta p is greater than equal to h cross, or delta y into delta py greater than equal to h cross, delta z into delta pz greater than equal to h cross. So the point in phase space is delta 6v, that is delta x, delta y, delta z, delta px, delta py, delta pz, delta 6v. If you multiply all these three equations, delta 6v is greater than equal to h cross. So the point in phase space is a 6-dimensional cell. This is also called quantum box. This 6-dimensional cell is called quantum box, and its volume is of the order of hq. So particle the phase space can be located somewhere in a cell having a location xyz and px, py, pz instead of a fixed point. In classical mechanics, we represent the particle in a fixed point, but here we locate it in a cell having whose size is described by x, y, z, px, py, pz. What does it indicate? This indicates we have 6-dimensional space on which we can represent the state of a particle, and the ensembles which contains large number of particles. This gave an idea that the uncertainty principle is used for ascertaining the number of quantum states. We shall use Schrodinger's equation to examine the situation, that is particularly in one-dimensional box. So let us consider one-dimensional Schrodinger's equation. What is one-dimensional Schrodinger's equation? That is d square u by dx square plus 2m by h cross square e minus v u is equal to 0. If it is a free particle, we know quantum mechanics, then v is equal to potential energy term is equal to 0. Since we are considering the one-dimensional box, the particle is capable to move within 0 to L, or value of x is limited between 0 to L, where L is length of the particle. So this equation, when v is equal to 0, the particle is free to move, that is d square u by dx square plus 2m by h cross square e minus v u is equal to 0 takes the shape d square u by dx square plus 2m e by h cross square into u is equal to 0. And you can find, if you plot a graph one-dimensional box at L, a graph between potential energy, potential V versus X takes this shape. And in quantum mechanics, you know the solution of this particle in one-dimensional box is u is equal to a sin kx plus b cos kx, where k square is 2me by h cross square. And you come across this situation, the total energy of a particle in one dimensional box is n square pi square h cross square by 2 ml square. When you calculate, considering the quantum mechanical equation of a particle inside a box, then and you consider the uncertainty principle, what you got? You got that the postulates of equal a priori probability can be used in quantum statistical mechanics. Why? Because they are used to explain the macrostates and microstates in quantum mechanics, which was discussed in classical statistical mechanics. So what is Heisenberg's uncertainty principle? If P and Q represent the position of a system, P is momentum and Q is coordinate, generalized coordinate, then delta P into delta Q is greater than equal to h cross. And the most striking features of the Heisenberg uncertainty principle is indeterminacy, which introduces the quantum mechanical state. Because Heisenberg's uncertainty principle tells we cannot determine the position and coordinate in a perfect manner, simultaneously in a perfect manner. So we introduced quantum mechanical state. We introduced quantum mechanical state because the position and momentum coordinates are in a dynamical state. So we explain them by a wave function. Let psi is a function of qt, is a dynamical state or a composed particle state. Let the state have a zero spin. So the particles can be represented either by q1, q2, q3 positions up to say qs, and corresponding momentums are p1, p2 and ps. If psi is the wave function which represents this, then psi star gives your probability density. So what will be the normalized condition? That is integration psi star qt psi qt dq is equal to 1. That means psi satisfies the normalized condition. And in classical mechanics, the dynamical state may be visualized as a point in dynamical space or Hilbert space. The Hilbert space, we know, classical physics we tell it as infinite dimensional space. So the time in quantum mechanics, its time evolution is described by Schrodinger's wave equation, that is IH cross del psi by del t is h psi, where h cap psi you can say that is a Hamiltonian operator. And the classical Hamiltonian, we know p square by 2m plus u, that p square by 2m can be written as minus Hamiltonian operator minus h cross square 2m sum over I is 1 to s states, s stands for states, del square by del qi square u q1 up to qe. So what does it indicate? It indicates the for an isolated system, the Hamiltonian is independent of time or a time independent. Hamiltonian is time independent. Hence, for the requirement the Hamiltonian operator, we consider a wave function having which is a function of the variables q1, q2, qn. It implies the function also dependent on time t. So we say psi is a function of qt. It indicates the same quantum mechanical dynamical state is possible, can also be used in classical mechanics. If you go through the time evolution of the wave function in certain examples, you will also find the same thing. Suppose we will consider an macro state. Then in that case, considering this time evolution, you can calculate the density matrix of macrostates. How can we calculate the density matrix? Let us consider an ensemble and border N0, big N0 is large number of identical particles. So the characteristics of the system are, first one, N0 must be large, that must be much greater than 1, N0. Second characteristics, they have common Hamiltonian. And Hamiltonian operator, as we have written AOP as an operator, so Hamiltonian operator is written as HOP. If Ri is a position vector, then at any time t, the physical state of the system is represented by a wave function psi, which is a function of Rit. So corresponding to item 3i, psi dash Rit denotes the normalized wave function, and that represents the state in which we have ith system of ensemble exists. So what are the characteristics of the system, macro system? First one, number of particles is much greater than 0. They have a common Hamiltonian operator. If Ri is the position vector, then psi Rit, psi, which is a function of Rit, represents its wave function, and the wave function is normalized. When wave function is normalized, we can calculate the probability of the particle. And the probability of the particle indicates that the wave function can be acceptable if it is normalized with help of multiplication of a constant, as we have done in Lagrange's multipliers by multiplication of lambda. So the time variation that is psi dash t can be written as, let us consider the psi dash t can be written as psi is a n dash t phi n. What is a n dash? A n dash, the amplitude part, psi n dash wave function is obtained when a n dash t multiplied by phi. What is a n dash t? That is equal to integration phi n star psi star t into d tau is volumes. D tau is configuration volume or very small volume. So what we find, when we are able to calculate the amplitude of that, we are able to calculate the probability. So let us take the help of our Schrodinger's equation. What is that one? If you multiply IH cross d by dt on both sides of this equation, you remember this equation? This is the equation. A n dash t is phi n star psi dash t d tau. D tau is configuration volume. This is phi n star psi n dash t is equal to a n dash t phi n, and this is psi dash t d tau. So when you take this IH cross del by del t on both sides of this equation, it takes the shape IH cross phi n star d by dt psi star dash t d tau. And finally, d by dt is taken, IH cross is here, this factor is called Hamiltonian operator. That is phi n star HOP psi dash t d tau. So we can write it as HMN, which is the sum over HMN A M dash T. What does it indicates? HNN is phi n star H Hamiltonian operator phi m d tau. So what is physical significance of A n dash T? It certainly indicates the amplitude or probability amplitude. And A n dash T mod square represent your probability, and ANT represent probability amplitude. Now, under this properties of, we can explain the density operator matrix. Now, density operator matrix, as we have discussed in case of classical physics or classical ensembles, For quantum ensembles, we can define. For a density operator, rho mn, which is a function of T, the density matrix element is represented as 1 by n0. N0 is a large number of particles of an ensemble. Integration, a summation, I stands from 1 to n0, that is a m dash t, that is time evolution amplitude part, and a n dash star t. So the ensemble average, this a m t and a n star t, this represent ensemble average. And the density matrix rho mn T is 1 by large number of particles of the macro system n0, summation I is 1 to n0, am dash t, an dash star t, where amt into ant, one is the amplitude part and the product represent the ensemble average. So rho mn, and when rho mn is this, if m is equal to n, you got rho nn, that is called your diagonal part of the matrix, that represents the diagonal matrix. So what is significance of rho nn? Summation rho nn is 1. That means the diagonal matrix is 1, which indicates we can easily derive the quantum Liouville's theorem by considering this density matrix and the properties of the density matrix elements. So our next course of discussion is quantum Liouville's theorem. You know the classical Liouville's theorem yesterday. And now we will discuss quantum Liouville's theorem. The quantum Liouville's theorem, if A is any operator, is represented by A ddt of expectation of A, is dA by dt, is del A by del T, dA by dt is del A by del T plus 1 by IH cross psi. This is Poisson's bracket of AH into psi. Yesterday we have discussed in terms of rho. So A does not explicitly depends on time, remember. Here A does not explicitly depend on time. That's why we can say d by dt expectation of A in quantum case, the Liouville's theorem takes this shape 1 by IH cross psi Poisson's bracket of AH psi, or this can be written within the psi of AH psi. So from this we know the classical Poisson's equation. From this one you compare, if rho is replaced, A is replaced by rho cap density matrix, and this is 1 by IH cross rho H. This is not X, this is your rho H, this is not the matrix element, rather it is Poisson's bracket in quantum mechanics, in classical mechanics. In quantum mechanics, this represent a Poisson's bracket. This represent a matrix element, but here rho H represents your Poisson's bracket. D rho by dt is 1 by IH cross rho H. So operator A is replaced by rho. Hence, this is your quantum Liouville's equation. Mind, this is the difference. We can write the quantum Liouville's equation, that is only difference is 1 by IH cross. D rho by dt is Poisson's bracket of rho H divided by 1 IH cross. So the quantum form of Poisson's bracket now is not rho H brought to rho H with respect to P and Q, that is also changed to your commutation bracket. Yesterday we have discussed that when a rho is constant, del rho by del T is 0, and the density operator takes the shape of this shape, that rho is constant, del rho by del T is equal to 0. We understand that we have three types of ensembles. So in the next way, we will calculate the density operator for each state, for each ensemble, canonical ensemble, microcanonical ensemble, and grad canonical ensembles. Our next discussion is quantum statistical ensembles. That is canonical, microcanonical, and grand canonical ensembles. Here, what we do, we relate the density matrix to ensemble theory with respect to the quantum mechanical indistinguishability state. Classically, we have distinguishability, but here we have distinct features of indistinguishabilities. So the first one is, let us introduce this Schrodinger's equation. Why we will introduce this Schrodinger's equation? Because at low densities and high temperature, all physical systems behave asymptotically, which was expected classically. We expect something classically, but when a temperature is very high and density is low, all physical systems undergoes an asymptotical behavior. So we introduce a Schrodinger's equation, that is h of psi kt is IH cross psi kt. For a complete set of orthonormal function, psi kt is a n kt, this is your amplitude part, into phi n. What is a n kt? We have earlier described in the last section, that is phi n star psi kt into theta. This is here phi n star is the complex conjugate of phi n, this phi n, and theta represents the small volume element of coordinate space, such that they satisfy this equation. Probability is equal to 1 summation a n k t whole mod square is equal to 1, which is true for all k. And the density operator, in this case, the density operator or defined by a matrix element. Density operator is rho mn, which is a function of t, is 1 by n summation k is 1 to n am kt an k star t. So it indicates that the matrix element is the ensemble average. I have told you am kt an k star t, this is the ensemble average of amt an star t, this is the ensemble average. So rho mn represent ensemble average of that quantity. Now when we consider the state is in equilibrium, the ensemble is stationary. When the ensemble is stationary, Liouville's theorem tells us del rho by del t is 0. Here, that means here we have considered the density matrix rho mn. So rho mn dot or del rho mn by del t is equal to 0. And it indicates that in this condition, when a density matrix is equal to 0, the Hamiltonian, we can diagonalize the Hamiltonian in this manner. That is, Hmn is En delta Mn. This is Hamiltonian, and the density matrix rho Mn is rho n delta Mn, such that you can exchange the rho Mn, which is a density matrix, is a symmetric matrix. That means rho Mn is equal to rho Nm. And physically, why the symmetry arises? Why density matrix is symmetric? This is because the symmetry is due to the statistical equilibrium, and it is counterbalanced equally by strong tendency to switch between same states in a reverse direction. This condition is of detailed balancing is essential for maintenance of equilibrium distribution within the ensemble. So we consider a physical quantity G, we take its expectation value, and the expectation value of this physical quantity G operator is written as expectation G. As earlier we have defined, for large number of operators, this is 1 by n, summation k is 1 to n, and psi k star G psi k theta, where the coefficient is your a n k and G expectation can now be written as, because psi is equal to a n k, phi n star, phi n becomes 1. So this is 1 by n, a n k star, a n k, G n m, and a n k, a m k represent your ensemble average. So in GNM with the new physical quantity is represented as integration phi n star G phi m theta. Now we can introduce the density matrix as a trace of an operator. That is how now this G expectation is the trace of rho G divided by trace of rho. Here rho is your density matrix and G is any physical operator. So the expectation of G is the trace of rho G divided by trace of rho. Similarly, we can move to explain microcanonical ensemble. As we have defined macro states and micro states, we now go to explain three types of microcanonical ensemble, and in each ensemble we will show what is the density matrix, what is the form of density matrix. So we know the density matrix is symmetrical, and in microcanonical ensemble yesterday we have discussed the energy, number of particles and volume remain same. And the corresponding thermodynamical macro state is represented by the omega, which is a function of A and VE. And the equal a priori possibility suggests they have various accessible states, where the same density matrix, symmetric density matrix, can be taken into account. And recall yesterday we have taken this equation that rho n is 1 by omega for each accessible state, and rho n is equal to 0 for other states. So the normalization condition which arises is written by, we know this thermodynamic probability entropy relation, which is given by S is equal to KL n log omega. Here the total number of distinct accessible states is computed quantum mechanically. When you consider indistinguishability into account, then the Gibbs paradox condition arises. If omega is equal to 1, we can say rho mn is equal to m is equal to n, and the matrix is equal to rho nn, whose value is equal to unit. And otherwise, if m is not equal to n, that will be 0. So we can represent the density matrix, that is rho mn, by this equation. Rho mn is 1 by n summation k is 1 to n. N is total number of particles in the ensemble. This is amk into ank star, which is am into an star. Because all the values of k are now effectively equivalent, then rho mn square is rho ml into rho ln. So rho mn square is rho mn, which indicates that the matrix is capable to define the to diagonalize the elements, and we can also calculate from this expression the off diagonal elements as well as the diagonal elements. When you calculate this expression, the rho mn takes this shape, that is 1 by n summation k is 1 to n amk ank star, which is 1 by n. You take simply mod a square into e to the power I theta mk minus theta nk, and we keep this factor as a constant c. Expectation of all these things e to the power I theta mk minus theta nk. This expectation term in the bracket is your delta mn, which is called the microcanonical ensemble, and C, where C is a constant. This is the density matrix for microcanonical ensemble, where C is a constant and its value is 1 by n summation k is 1 to n mod a square. This factor is the value of the constant when we define a microcanonical ensemble density matrix. Similarly, we can explain the density matrix of a canonical ensemble and grand canonical ensemble. Let us take example of canonical ensemble. Let's have a macro state, and we know in canonical ensemble T, V and E are same. Temperature, volume and number of particles, NVT, okay, NVT remains same. So the For probability, we can choose randomly an ensemble whose energy is say ER. Randomly, that's why energy is ER. So we have a exponential minus beta ER is given by the total energy, total probability of the system. And beta is nothing but 1 by kt or k beta t, that is Boltzmann's constant. So the density matrix energy representation can be written as rho mn is equal to rho n delta mn. What is rho n? Rho n is c exponential minus beta en, and c is a constant. Hence we know what is the c. C is, yesterday we know c is 1 by sum over n e to the power minus beta en, which is 1 by qn. Remember, yesterday we have taken classical partition function, symbol is z. But here we consider the quantum mechanical partition function of canonical ensemble is given as qn beta. Qn beta is the partition function for quantum mechanical canonical ensemble. Yesterday we have considered z. So the density operator rho is equal to here sum over n phi n 1 by qn beta e to the power minus beta en. This is ket phi n and this is bra phi n. So this is 1 by qn beta. Qn beta represents your partition function into e to the power minus beta h, and this is sum over phi n, ket and this one. So if you calculate this one, what will you obtain? You will obtain the same partition function, and under classical limit, the quantum partition function under a limit n tends to infinity becomes the classical partition function. And the suffix n used here emphasizes that the average is taken over all ensembles and where n is fixed. So what we do, we are able to write the form of this form of density matrix for canonical ensemble, and we are capable to write what is the classical partition function, what is canonical ensemble partition function for quantum statistics. Next is for grand canonical ensemble, we can write the density operator rho cap. Rho cap is a density operator in Hilbert space with infinite number of particles. Now the density operator must commute with the Hamiltonian operator. So we must write first, in order to prove this, we must define first what is the density operator for a grand canonical ensemble. The grand canonical ensemble density operator is represented as rho cap, that is 1 by q0, which is a function of mu vt. Yesterday we have told the grand canonical partition function is a function of chemical potential, volume and temperature. So that is z is a function of mu vt, but z grand canonical we take gc, but today that is converted to 1 by q0 grand canonical function, which is a grand canonical ensemble, which is a function of chemical potential, volume and temperature, e to the power minus beta. Beta is 1 by k beta t, t is temperature, and k beta is Boltzmann's constant, h is your Hamiltonian, minus mu is chemical potential with n cap. So you can write the expression for a grand canonical partition function. If this is grand canonical density matrix, this is grand canonical partition function, that is q0, which is a function of mu vt, is e to the power minus beta er. This is energy ER minus mu Ns. R stands for energy of the reservoir, S stands for energy of the system. So this is number of particles of the system, Ns, mu is chemical potential, and this is nothing but a trace of e to the power minus beta. In ER, we have written Hamiltonian H minus mu N. So when you know the density matrix, we know the partition function of grand canonical ensemble, we can write its ensemble average. The ensemble average is written as G is equal to 1 by Q0 mu Vt, that is 1 by grand canonical partition function, is you trace of this quantity, trace of G cap E to the power minus beta H cap into E to the power mu beta N cap, which is nothing but Z to the power N, your classical partition function, 1 by Q0, this one, this is classical partition function Z to the power N, expectation of Gn, Qn beta divided by Z to the power N, Qn beta, and summation is from 0 to infinity. Where this Z is equivalent to E to the power minus beta mu. It is called fugacity of the system. You find this Z, this is called fugacity of the system, and Gn is your canonical ensemble average. So the quantity Q0, which is a function of mu0 Vt, is a grand canonical partition function. Hence, we are able to write the density matrix for canonical ensemble, for grand canonical ensemble, for microcanonical ensemble. Similarly, we write their partition functions, and we are able to calculate the ensemble average in all cases. Let's have an example. We will consider a free particle. Why we consider a free particle which travels in a one-dimensional box? Then what will be its Hamiltonian? If we consider it is a free particle, any free particle has zero potential energy. When potential energy is zero, what is Hamiltonian? Hamiltonian is p square by 2m, that is minus h cross square 2m delta square. That is minus h cross square by 2m del square by del x square, del square by del s square, del square by del z square. So the eigenfunction of the Hamiltonian satisfies the periodic boundary condition in this case. That means what is length of the box? Length of the box moves from 0 to L. If we have a box, its length is 0 to L. So it satisfies the periodic boundary condition, that is phi of x plus L y z is phi of x y plus L z, phi of x, this one, x plus L y z, or x y plus L z, or x y z plus L, that is phi x y z. That means periodic boundary condition phi of t is equal to phi of t plus 2 pi, so on. Here 2 pi stands for L. So the state is represented by phi r, phi er is 1 by L to L is length of the box into e to the power ikr. What is k? K is a wave vector. How it is represented? That is kx into x cap, ky into y cap, plus kz into z cap. And the corresponding position vector r is x cap, y cap, and z cap. So when particle is in a box, its energy, we know earlier, that is h cross square k square by 2m in quantum mechanics. And corresponding wave vector k is represented as k is equal to 2 pi either kx or ky or kz, that is equal to 2 pi by L nx ny nz. What is n? N is a vector with integral components, that is 0, plus or minus 1, or plus or minus 2. So now we can evaluate the density matrix rho of the system. How can we evaluate the density matrix rho of the system? The density matrix is essential to explain the energy as well as state in quantum mechanical ensembles. So we represent this. This is this matrix in the matrix element form, e to the power minus bh r r dash. which gives rise to a value e to the power minus beta e, that is phi er, that is energy E in the position R, and this is its complex conjugate, that is phi star E R dash. Then you got this equation, the total matrix R e to the power minus Bh, this expectation becomes m by 2 pi beta h cross square to the power 3 by 2 into e to the power m by 2 beta h cross square r minus r dash square. So at this stage, we use two integrals. One is integration cos kx e to the power minus gamma k square dk is equal to root 2 over pi by y e to the power minus x square by 4 gamma. And integration minus infinity to infinity sin kx e to the power minus gamma k square into dk is 0. So what will be its trace? And the trace of e to the power minus beta h, this factor, that is trace of e to the power minus beta h, this is equal to r e to the power minus beta h r dqr, which is v is equal to m divided by 2 pi beta h cross square to the power 3 by 2. So we can identify that by dividing the density matrix, the desired density matrix, instead of e to the power minus beta h, we can use r rho cap r dash बंद कर मगर ताले r rho cap r dash is 1 by v e to the power minus m by 2 beta h cross square r minus r dash square. So we explored this is a property of density matrix, and in the light of symmetry we can find the expression for the diagonal and off diagonal elements of the density matrix. Okay, so this is all about the ensemble theory, quantum statistical ensembles. Next we will go to Bose-Einstein and Fermi-Dirac statistics. One is Bose-Einstein statistics and Fermi-Dirac statistics. I have told you Bose-Einstein statistics was developed in 1924 with bosons, and Fermi-Dirac statistics was developed by your Fermions in 1926. That is by Pauli exclusion principle. So the particles which obey Pauli exclusion principle are fermions. The particles which do not obey Pauli exclusion principle are treated as bosons. One are fermions, the others are treated as bosons. Fermions are spin half particles, while bosons are your integral spin particles we have discussed. And the fermions, the particles of bosons are photons, phonons, etc. And fermions are electrons, protons, neutrons, and such on. They are fermions and bosons. The Fermi-Dirac statistics and Bose-Einstein statistics they are called quantum statistics. And these statistics are needed to explain the indistinguishable particles, which explains the black body radiation and the symmetry concept. That is, if we have a wave function psi, which is this wave function of particles 1 to 3, that is position r1, r2, r3. If psi r1, r2, r3 is equal to psi r plus psi r1, r2, r3, then we say this is psi r2, r1, r3 is plus psi r1, r2, r3. Then we say the wave function is symmetric. If it is minus psi r1, r2, then we say this is antisymmetric wave function. When you consider symmetric and antisymmetric wave function, then we have two distinguishable wave functions. One is symmetric part is bosons, and antisymmetric part is your fermions. So this is a table which indicates the particles of bosons and fermions. These are spin angular momentum particles, bosons, 0. Angular momentum is h cross, 2h cross, 3h cross, and it does not obey Pauli exclusion principle. Bosons have wave function which are symmetric. They are photons, phonons, deuterons, pi mesons, He4 nucleus. And fermions are half integral particles, that is h cross by 2, 3h cross by 2, 5h cross by 2, obeys Pauli exclusion principle. They are antisymmetric. I have told electrons, positrons, neutrons, muons, protons are treated as this one. Now we will go to Bose-Einstein statistics. So what are first postulates of Bose-Einstein statistics? First one, Bose suggested particles are identical and hence indistinguishable. First postulate of Bose-Einstein statistics, particles are identical, hence indistinguishable. Second one is Heisenberg uncertainty principle and Pauli exclusion principle are not applied to Bose-Einstein statistics. First thing, particles are indistinguishable. Second thing, Heisenberg uncertainty principle are applied to bosons, but Pauli exclusion principle are not applied. Again, Heisenberg uncertainty principle are applied to bosons, but Pauli exclusion principle are not applied to bosons. Third one is there exist number of quantum states for a given energy level. For a given energy level, there exists a number of quantum states, and the number of bosons occupy a given quantum state. That means there is no a priori restriction in this regard. Suppose number of particles in a ith quantum state is bold n I, such that summation Ni is n, summation Ni is n, and summation delta Ni is 0. Since the particles are non-interacting, so total energy U is constant, so delta U is equal to 0. These are the assumptions. Now we must consider all the quantum states have equal a priori probability, and let Gi is the number of states having energy Ei. Gi is the number of states having energy Ei, so that the problem is to distribute them, Ni number of particles, indistinguishable particles in Gi quantum states. So what is number of indistinguishable particles in Bose-Einstein statistics? Ni particles. In how many quantum states this will be distributed? This will be distributed in Gi quantum states. And no restriction is imposed of number of particles which will occupy Gi states. So we apply a particular trick to explain this one. That means Gi plus Ni will be quantum states. The Gi quantum states, Ni number of particles. So total objects is Gi plus Ni. When total objects are Gi plus Ni, we have permutation and combination principle. So what is permutation? What are total number of meaningful arrangements? That will be Ni plus Gi minus 1 factorial. That is number of meaningful arrangements will be this divided by number of meaningless arrangements. Or you can say the number of meaningful arrangement is Ni plus Gi minus 1 factorial divided by number of meaningless arrangement means Ni factorial into Gi minus 1 factorial. So this is by permutation and combination. Hence we write the thermodynamic probability omega in this manner. Ni plus Gi minus 1 factorial. This is number of meaningful arrangements divided by number of meaningless arrangement. What is number of meaningless arrangement? That is ni factorial into gi minus 1 factorial, where I corresponds to ith energy level. And the thermodynamic probability of the system is the total number of ways of distribution of n particles in n energy level. That is given by, you know, the expression omega is the sum over continuous product from n energy states. I stands from 1 to n, ni plus gi minus 1 factorial by ni factorial into gi minus 1 factorial. Now, the most probably distribution can be written as distribution of Bose-Einstein can be written as by this, that is omega, which is sum over continuous product ni plus gi factorial divided by ni factorial into gi. This is by Stirling's approximation, that is log n factorial is n log n minus n. So we consider the Stirling's approximation. We apply and find this equation. Log omega is log ni plus gi factorial minus log ni minus log gi factorial. And in this, with proceeding in this manner, the most probably distribution function, we find that d of log omega be, this must be equal to 0. Here we have replaced the thermodynamic probability omega by Bose-Einstein thermodynamic probability, that is omega be. As a result, we obtain the log delta of log be is log gi plus ni delta ni. You are using this one, this equation, then this ni into delta ni plus gi plus ni by gi plus ni into delta ni minus ni into 1 by ni delta ni minus delta ni into log ni. Here the second term, this term, and this third term, they cancel each other. If this cancels, this is delta ni, this is ni cancels minus delta ni. So the expression is only first term and fourth term lies. That is delta of log omega b, delta ni log of ni plus gi minus ln. That is minus ln ni by gi plus ni delta ni. So for equilibrium, we can write that log of ni by ni plus gi delta ni is 0. Now we apply equation of constant, that is delta ni is 0. What is this one? Now delta of epsilon I ni is equal to 0. These are two constants. So epsilon delta ni is 0. So here epsilon I are invariant and they maintain a linkage with the earlier equations. So delta ni log of ni by gi plus ni plus alpha plus beta epsilon I 0, or you say this factor in the bracket is equal to 0, or you solve it, this is log of this minus alpha minus beta epsilon I is equal to 0, and you can find this log of 1 plus gi is alpha plus beta epsilon I. When you take antilogue, you get 1 plus gi by ni is e to the power alpha plus beta epsilon I. And f of this f of epsilon I, this gi by ni is called your occupation index, and this is written as f epsilon I, that is Bose-Einstein distribution law, ni by gi is 1 by e to the power alpha e to the power beta epsilon I minus 1. At a very high temperature, the particles are distributed over a wide range of energy. So we say that if gi is much at a very high temperature, the energy of the particle is very high. According to Bose-Einstein case, when temperature is very high, there is a wide range of energy. So number of particles in the wide range is much less than the number of quantum states. Number of particle is much any range is much less than number of quantum states. So Gi is much greater than Ni. Hence the upper equation, hence this equation, that is a log Ni plus Gi by Ni minus alpha minus beta epsilon I. This equation takes the form log Gi minus log Ni minus alpha minus beta epsilon I 0. Or f of epsilon I is 1 by this one, or e to the power minus alpha, e to the power minus beta epsilon. What is beta? We have told beta is equal to 1 by k beta t. Hence, this is called your Bose-Einstein distribution formula. And next is, we are capable to derive Planck's distribution law by considering Bose distribution formula. What is Planck's formula? Which is true for both wavelengths of a black body, that is in the lower frequency range and the higher frequency range. We assume that there are a large number of oscillators, each oscillator having energy epsilon is equal to h nu. And in the frequency range nu and nu plus d nu, the energy density is given by u nu d nu is 8 pi nu square by cq into h nu by e to the power h nu by k beta t minus 1 into d nu. So Bose applied statistical mechanics to explain the black body radiation, that is Planck's law, derive Planck's law of radiation. He assumed that within an energy range E and D and frequency range nu and nu plus D, the number of quantum states will be GE into D. So number of particles in that range will be, if GE, DE, number of quantum states within energy range DE and frequency range nu plus d nu, that is frequency range d nu, and number of particles is n number of particles having energy E. Here n number of particles have energy E, and within range n E and E plus D, this is total number of particles Ne into D, energy associated with each particle. That is number of quantum states GED divided by e to the power alpha into e to the power e divided by k beta t minus 1. We know number of quantum states in a momentum range p and p plus dp is given by this one. Gp dp is 8 pi vp square by hq into dp. This was derived in thermodynamics. And energy of each photon E is equal to h nu. Momentum of a photon is h nu by c. Change in momentum is h by c into d nu. So when you substitute these values, you obtain the number of quantum states between the frequency range nu and nu plus d nu. G nu d nu is 8 pi v by cq into nu square d. So in a cavity, there is an assembly of photons in the heat reservoir at temperature T, and the photons continuously emit energy. And those energies are absorbed by the walls of the container. So number of particles are not conserved, which means the delta Ni is not equal to 0. We have assumed delta Ni is equal to 0, but here delta Ni is not equal to 0. Now the number of photons with frequency range nu and nu plus d nu can be written as, since we have written Ned is G d by e to the power this, so n nu d nu is G nu d nu by this one. And this equation within a certain volume gives a value n nu d nu is 85 v by cq into v square by 2h nu by k beta t, sorry, nu square by 2h nu by k beta t minus 1 into d. So in the given volume, we know energy of a photon in the frequency nu is h nu. So in the frequency range d nu, we can write, and in a given volume, the energy density u nu d nu is h nu by v n nu d nu. This is called the energy density, and u nu d nu is your h nu by v. The value of nv we have calculated here. The nv is your this one, NVDV is this, so NV is 85V by CQ into nu square by e to the power h nu by k beta t minus 1. When you put this value, you got the Planck's radiation law, that is u nu d nu is 85h by CQ nu q d nu by e to the power h nu by k beta t minus 1. Hence, Bose-Einstein's equation is capable to explain, to derive the Planck's black body radiation, which considering the particles are indistinguishable. The next one is Fermi-Dirac statistics, which was developed considering the fermions. So what are the basic postulates of Fermi-Dirac statistics? Or the fermions, which are spin half particles or spin integral particles. Particles are identical here and indistinguishable. Same thing that in Bose-Einstein. But the second condition, in that case, Heisenberg uncertainty principle was obeyed, but Pauli exclusion was not obeyed. But here, Heisenberg uncertainty principle is obeyed, as well as Pauli exclusion principle is obeyed. That means the fermions obey both of them. As a result, there exists a definite priori restriction on occupancy. Remember this line, there exists a definite priori restriction on occupancy. There cannot be simultaneously more than one particle. Remember, there cannot be simultaneously more than one particle in any quantum state. This is important. No more one particle is possible in one quantum state with all quantum numbers same. So the state would either remain empty or can be contained in fermion. Hence they assume that the numerical part is sum over delta ni is 0 and sum over delta u is equal to 0. So when you proceed to explain thermodynamic probability, as we define, we consider define in Bose-Einstein statistics, we consider n particles which are indistinguishable, which are non-interacting and obey Pauli exclusion principle. Let the number of particles say nn. Nn means n1, n2 up to nn. Nn number of particles. And what is the energy? Energy of first particle. N1 number of particles having energy epsilon 1, N2 particles have epsilon 2, and Nn particles have energy epsilon n. And here we define a term Gi. It represents multiplicity degeneration of the energy level. Then the thermodynamic probability for Fermi-Dirac statistics is written as omega I is Gi factorial by Ni factorial into Gi minus Ni factorial. I have told you that in that case we have discussed this is number of meaningful arrangements divided by number of meaningless arrangements. Here in Fermi-Dirac statistics we discuss the fermions, which are indistinguishable particles, and the no two particles can occupy the same state in the same time. That's why we defined this omega, which is a function of n1, n2 all particles, which is the sum over, that is Gi factorial by Ni factorial into Gi minus Ni factorial. Remember, in Bose-Einstein statistics, we have written this expression as this is Ni plus Gi minus 1 by Ni factorial into Gi minus 1 factorial. Here in the numerator, there was Ni plus Gi minus 1, but here Gi factorial only. In the denominator, Ni factorial, here Ni, and Gi minus 1 is replaced by Gi minus Ni factorial. So total number of independent ways of obtaining the is sum over continuous product. Omega I is omega Fermi-Dirac, seti omega Bose-Einstein B, that is Gi factorial by Ni minus Gi. Now, when we know the thermodynamic probability, we can find the most probable distribution of Fermi-Dirac distribution function we can derive. So consider the log of this equation, log of this, take log of this one. This omega Fermi-Dirac is gi factorial by ni factorial minus gi minus ni. You take log of this one. That is log gi minus log ni minus log gi minus ni factorial. In each case, you apply Stirling's approximation, that is log n factorial, n log n minus n. When you, in each case, you apply Stirling's approximation, you got log of omega fd is gi log gi minus ni log gi minus gi minus ni log of this one. Here, these terms, second, fourth, and sixth terms, they cancel. That's why you got that result. And you use the condition that is delta omega, that is delta log omega is 0. So delta log omega Fermi-Dirac is equal to 0. That means delta, this is log of Fermi-Dirac is g, delta gi log gi minus ni log ni plus ni minus gi log is 0. As in case of Bose-Einstein distribution, Nij are very vary continuously and Gi is not subject to change. Hence, we get this expression that is minus Ni into 1 by Ni delta Ni. This is delta Ni, cancels with this term Ni minus Gi by Gi minus Ni into delta Ni. First and third term cancels out. Only second and fourth term gives the contribution delta log of this is minus log Ni by Gi by Ni into delta Ni. Since the left hand side is 0, that's why the right hand side log of Ni by Etika is 0, which indicates this is a Fermi-Dirac distribution function. This indicates this is a Fermi-Dirac distribution function. And we define this Fermi-Dirac distribution function in the term Fermi-Dirac distribution f epsilon I, which is Ni by Gi. Remember, Fermi-Dirac distribution function is your, for Fermi-Dirac distribution function, we define this occupation index, Ni by Gi, 1 by e to the power alpha, e to the power epsilon I by k beta t plus 1. That means the average number of particles in each quantum state is represented by continuous manner n epsilon d. This is the number of particles whose energy lies between epsilon and d epsilon is equal to Ge into d by e to the power alpha into e to the power beta epsilon I plus 1, which is G epsilon d epsilon e to the power alpha e to the power epsilon I by k beta t plus 1. And this represents number of particles whose energy lies between epsilon and d epsilon, where the quantity alpha is minus epsilon f by k beta t. Epsilon f is called Fermi energy. And the Fermi distribution function, now we can, this is most important one, Fermi distribution function, fd means Fermi distribution function with energy epsilon I is 1 by e to the power minus epsilon f by k beta t plus 1. Epsilon f is Fermi energy. So this distribution is for fermions and known as Fermi-Dirac distribution function. What are the Fermi energy? We have defined a term alpha is equal to minus epsilon f by k beta t. Epsilon f is Fermi energy. Let us discuss what is Fermi energy. We know at 0 degree, if you put here, if t is equal to 0, you put expression, so t is in the denominator. So this will be f Fermi-Dirac, this factor, if this is 0, e to the power 0, this is 1 by e to the power 0 plus 1, this is 1 subject to the condition epsilon I is less than epsilon f. And Fermi-Dirac function is 0 when epsilon I is greater than epsilon. If epsilon I is less than epsilon f, then this is called Fermi energy. if epsilon I is greater than epsilon f, then this Fermion Dirac function is 1, otherwise it will be 0. So what does it indicate? This is a step function. You compare it with step function. And the energy, if epsilon is less than epsilon f, then probability of occupancy of all the states is unit. Epsilon I is less than epsilon, Fermi-Dirac function is 1. That means probability of occupancy of all states. That means all particles will be occupied, and that is maximum 1. When epsilon is greater than epsilon f, then it will be 0. So Fermi energy corresponds to highest occupied energy level. What is Fermi energy? Fermi level corresponds to higher occupied energy level. And with increase in temperature, Fermi energy, Fermi Dirac distribution function changes from 1 to 0. And more gradually, so when t is greater than 0 and epsilon is equal to epsilon f, not greater than, not less than, then you will find this function. What will be this value? This function will be, when epsilon I is equal to epsilon f, this will be 0. E to the power 0 is 1. So Fermi Dirac function is 1 by, this is 1 plus 1, that is half. So Fermi Dirac distribution function is half. Just you consider, this will be the graph. This plot is very important, this plot. This one is Fermi Dirac function for t is equal to 0. Now that means when epsilon is equal to epsilon f, this is half. Fermi Dirac function value is half. And when you consider that t is equal to, this is t is 0 Kelvin. When t is greater than 0 Kelvin, this is the position of half, and this is maximum value 1, this is 0. The Fermi Dirac function varies from 0 to 1. And this is the critical value when energy is equal to Fermi energy. This is Fermi energy level maximum. At that condition, the Fermi Dirac function have half value. Otherwise, its value tends from 1 to 0. And this depicts in this manner 0 with energy, with increase in Fermi energy. So what is physical interpretation of Fermi level? Fermi level is the energy which probability occupancy at t greater than 0 is half, which means 50%, half means 50% of the quantum states. Here 50% of the quantum states in this Fermi level are occupied, and this 50% is empty, and this 50% is occupied. So we can say that in this case, if you consider the Fermi state energy f of epsilon with different temperatures T0, T1, T2, and plot a graph for different temperature, this is maximum value 1, this is half, this is 0, and this is how f of epsilon varies with energy. This is for T2 state graph, this is for T1 graph, and this is for T is 0. You can find T2 is greater than T1. When the temperature increases, you find this is this comes to the lower energy side, and when temperature is 0, epsilon is equal to epsilon f. This gives half, 1/2 of the energy, 50% of the energy plot is not occupied, 50% of the states are not occupied. So if you plot the number of particles versus energy, if epsilon is the energy, Ne corresponds to number of states with the energy epsilon, then the plot shows this manner for different temperatures. This is for temperature T is equal to 0 for epsilon f Fermi energy. This graph. When T is equal to T1, you have a graph of this one. When T2, we graph of this one. That means if temperature is not very large, what is the conclusion from this graph? The epsilon f varies rapidly. Temperature is not large, it varies rapidly. But when temperature is large, T2 is greater than T1, it varies slowly. That means at extreme low temperature, when epsilon is nearly you can find this is a step function. F epsilon is nearly a step function. The distribution, when F epsilon takes a step function, the distribution is strongly degenerate. And at higher temperature, the step-like picture gets distorted. The step-like picture is distorted at higher temperature. There is no step here. So we say the nearly non-degenerate. So degeneracy, strongly degenerate and nearly degenerate is defined by this plot. Now you can satisfy the this gives rise to some quantum states, and when the quantum states are occupied, and what are the Fermi levels and what is Fermi gas. When you consider the Fermi gas model, that is a free electron model, where we consider the Fermi gas differs from ordinary gas by two ways. One is it is charged with ordinary gas. Ordinary gas, it is charged, while ordinary gas is not charged. Fermi gas is charged. And the concentration of electrons in Fermi gas is very large. Normally, in ordinary gas, the concentration of electrons per unit volume is 10 to the power 25. But in case of Fermi gas, the concentration of electrons is of the order of 10 to the power 29 per meter cube and 20 to the power 25 per meter cube in ordinary gas. So concentration of electrons is more in case of Fermi gas. And in Fermi gas, we have the Fermi gases are charged, while ordinary gases are neutral. Hence, we consider what are ideal quantum states. Ideal quantum states, we consider the state of energy. Ns is the number of occupation number, that is Ns can be written as 1 by e to the power minus beta epsilon s minus mu plus k. If k is minus 1, this is your this corresponds to bosons, number of bosons. If k is plus 1, this corresponds to number of fermions. If k is equal to 0, you can find that is classical statistics or Maxwell-Boltzmann statistics. Hence, we represent the factor mu. Mu is your chemical potential that is given by the equation minus alpha k beta t. The number of particles in element of phase space, that is your dqr into dqp phase space, is the number of quantum states and the occupation number. That is given by the number of quantum states with energy epsilon is given by dqr dqp divided by hq. So that we obtain dn is equal to dqr dqp by hq multiplied by n. And it indicates the if you have a subsystem and distinguishable by internal properties such as angular momentum L of the gases, we denote such subsystems by a number g. In that case, this dn can be written as dn is g dqr dqpi by hq. So the energy of interaction between the particles making up the system is negligible, so small, and energy does not depend on the direction in which particles are moving. So dn can be written as g 4 pi v pi square dpi by hq into n epsilon. Here the momentum and energy of a non-relativistic particle is considered by the relation p square by 2m. And dn is the number of dn becomes equal to your c, this is 2 pi v 2m to the power 3 by 2 by hq into g into epsilon to the power half d epsilon e to the power beta epsilon minus mu plus k. And this factor in the bracket is c. The c is a constant here. This is 2 pi v 2 pi 2m to the power 3 by 2 by hq into g is a constant, and this expresses C expresses that this is a constant for number of particles, which is a function of energy, and that is called non-relativistic quantum gas. So the exponential factor you are finding here, this exponential factor e to the power beta epsilon minus mu plus k, this exponential factor in the denominator gives you a little value. So dn by d epsilon is proportional to epsilon to the power half. Or dn by d epsilon can be written as under high energy limit e to the power minus e beta epsilon. If you plot a graph, this is the graph for occupation number n epsilon with energy. This is dn by d epsilon. This is variation of energy for non-relativistic case, and this is for high temperature. This is number of particles, and variation of exponential term is dominated here. That's why at low temperature we have this plot, at high temperature we have this plot. These two plots indicates what is the consequence. These two plots indicates the occupation number and the distribution of particles. The total particles are different. And when you study this curve, we will consider this curve to calculate at what is the difference of acquiring particles in the low temperature state and high temperature state. And when we integrate from 0 to infinity range of energy, we get the total number of particles. N is equal to C is the constant, V epsilon to the power half d epsilon divided by e to the power beta epsilon minus mu plus a constant k. So what is change in energy? Change in energy of each particle is epsilon. If d change in energy, epsilon multiplied by dn. That is d is equal to Cv epsilon to the power 3 by 2 d epsilon by e to the power beta epsilon minus mu plus k. So total energy of the system will be obtained by integrating the expression over epsilon. And E is equal to Cv epsilon to the power 3 by 2 into d divided by e to the power beta epsilon minus mu plus k. That means total number of particles and total internal energy you find. Total energy remains similar. Total number of particles you find here. Total number of particles, you got the expression from dn, and you got the expression of total energy. They are quite similar. So what does it indicate? This indicates that since total energy is non-relativistic, total internal energy is also non-relativistic, and this represents a Fermi gas. So total energy, which is earlier, is 3 by 2 nkt, that k beta t, that is Boltzmann's constant, plus or minus zeta, which is a function of mu t. So this sign, plus sign is for fermions and minus sign is for bosons. So this is the expression for both fermions and bosons, the total internal energy of the system. So zeta, which is a function of mu t, is written as Cv integration n epsilon square epsilon to the power 3 by 2 into d. And the number n epsilon is very small. So it gives an at higher temperature range, and particle has a large density, and the range of energy is also large, the occupation number is also large. So we consider this function zeta, which is a function of mu t, can also under the fugacity condition, taking some mathematical expression under limiting condition also, it gives to quantum statistical neighborhood, gives to your classical neighborhood. Next one is our weakly degenerate quantum state. These are strongly degenerate quantum states. We have weakly degenerate quantum states. When we consider weakly degenerate quantum state, A is much less than 1. And in that case, In terms of fugacity, we can rewrite that equation. N is Cv epsilon to the power half d epsilon by 1 by a e to the power beta epsilon plus k. So to evaluate this integral, we assume here let beta epsilon, this factor is x. So beta d epsilon is dx. You put this value epsilon to the power half into d epsilon is x to the power half dx by beta to the power 3 by 2 k beta t to the power 3 by 2 into x to the power half into dx. And this gives rise to a factor that is n is Cv k beta t to the power 3 by 2 x to the power half into dx by 1 plus a e to the power x plus k. So by applying binomial expansion, we can write the number of particles, the total number of particles with mathematical calculations. You can find n is c constant, v is volume, k beta is Boltzmann's constant, t is temperature to the power 3 by 2. This is gamma function, gamma of 3 by 2 into a minus, this is large, some calculations are there, mathematical calculations, k a square a to the power 2 to the power 3 by 2 plus a cube plus this one, where a are fugacity. What is this a? A is fugacity. N is total number of particles, c is your constant, v is volume, k beta Boltzmann's constant, t is temperature, this is a gamma of 3 by 2, a is fugacity, this is a series, a minus k square by 2 to the power 3 by 2 plus a cube by 3 to the power 3 by 2 so on. So using this procedure of internal energy, total energy E is Cv k beta t to the power 5 by 2, gamma of 5 by 2, a minus k square by this one plus so on. This indicates the dependence of total number of particles and energy in a weak degenerate quantum system. And fugacity A or chemical potential mu or absolute temperature T, all are the number of particles and the energy depends on all these factors. So we can put if the fugacity for 0, when the energy is 0, A0 value will be n divided by Cv k beta t to the power 3 by 2 into gamma function gamma of 3 by 2. Or with simply we consider weakly degenerate states and temperature is high. So A0 can be written as, in terms of this one, A0 becomes NHQ divided by V into 2 pi mk beta t to the power 3 by 2 into G. Here we use the relation gamma of 3 by t is root over pi by 2. And what does it indicate? If you find, we can interpret this as A0 is 1 by G, H divided by V by N to the power 1 by 3, 2 pi mk beta t to the power half. So this is nothing here, H by 2 mk beta t to the power half is lambda de Broglie. This is called de Broglie wavelength. Hence, the fugacity is related with our de Broglie's wavelength and can be written as in the form that is A0 can also be 1 by G. So this is lambda de Broglie divided by your V by N to the power 1 by 3 is taken as N here. And we can express this fugacity in terms of this de Broglie's wavelength. Now we will discuss the conduction of electrons in metals. We know the electron gas, Drude, a scientist, suggested that electron gas is developed and considering the free gas is moving inside the metal. He suggested classical statistics and explained the electrical or thermal conductivities. He also explained the thermionic emission and the photoelectric emission, how it takes place. So he defined the fermionic gas in terms of and suggested the energy of it is E is equal to 3 by 2 nk beta t into 1 plus k a0 by 2, where a is a constant that is 1 by 2 to the power 3 by 2, a0 is your fugacity. And in this case, the Cv, which is your heat capacity at constant volume. We know the expression Cv is dE by dt at V. Then the total energy, if you put there, then the total energy expression will be 3 by 2 n k beta t plus additional factor will be 3 by 4 Ka n k beta t alpha into t to the power minus half. So we consider the free electrons are capable to move inside the atom, inside the metal. When you consider strongly degenerate Fermi gases, so the occupation index for strongly degenerate Fermi gas n is summation ns 1 by e to the power beta minus epsilon s by mu plus k, which is 1 by a to the power minus 1 e to the power beta epsilon s plus or minus 1. And you consider this factor plus or minus 1 is for your minus a is less than when epsilon 1 is 0, the occupation number will be positive, and for a is less than 1, less than or equal to 1. If a is greater than equal to 1, then this will be minus 1. If this factor ns is 1, then a must tend to infinity. So for strongly degenerate systems, we find the Bose-Einstein and Fermi-Dirac systems will be vastly different and cannot we treat together as in case of weak degenerate states. In strong degenerate state, they are completely separable. So if you consider the Fermi-Dirac distribution function for completely degeneracy, then the Dirac function, the NFD, that is number of occupation number for Fermi-Dirac with energy epsilon, is 1 by e to the power minus epsilon minus mu k beta t plus 1, and this becomes equal to this value. And Cv 0 to epsilon a Fermi energy epsilon to the power half d epsilon. So this is how they are occupied. This is initial state. This is epsilon by mu n epsilon, and this is for different plots. This is occupation number of as a function of energy. This is for completely degenerate states Fermi gap. And the completely degenerate, this is for a glass of water. This looks like a glass of water filled. The distribution can be compared with this like a glass of water. And it states above Fermi energy level, we have empty states. If this is Fermi energy level, that is which is half Fermi level, epsilon is equal to epsilon f, we have a completely empty states. And the total Fermi energy is given by h square by 8m 3n by pi v to the power 3 by 2. So corresponding Fermi temperature is given by Tf is epsilon f by k beta, which is h square by 8 m k beta 3n by pi v to the power 3 by 2. Tf is temperature, Fermi temperature, epsilon f Fermi energy, k beta Boltzmann's constant, h is Planck's constant, n is number of states, and v is your volume, m is mass of each particle. So for different elements, we have different temperatures, and we have different Fermi energy states. If we consider a specific example for a potential well, what is the relation between work function and the Fermi energy? This is the relation. If this is the work function, this is Fermi energy, and half part of it is half part of this one is not field, but lower part is field. That is field like this one. The horizontal line depicts the field energy level. This is up to this the energy is field. Up to this no energy is there. So we know the work function Einstein's equation that h nu is equal to w minus phi 0. Phi 0 is work function of the metal. That is minimum amount of energy required to dislodge the electrons from the surface of the metal. Hence, we are able to find, if you plot a graph between Fermi distribution function versus energy, I have solved this graph, but for different potentials. This graph is for different temperatures, the corresponding to different chemical potentials, mu1 and mu2. This graph shows this is for Bose-Einstein state, and this is for Fermi-Dirac state. This is plot of Fermi-Dirac function. This is Bose-Einstein function versus energy for different temperatures. This is for fermions and this is for bosons. And under this condition, you will find the fermions and bosons, they plays different roles at which is dependent on different temperatures. If you have a summary of this, we can say of the three statistics we can compare that what is the nature of the particle. Nature of the particle, these are distinguishable. Maxwell-Boltzmann particles, Bose-Einstein and Fermi-Dirac, they are indistinguishable particles. And if you compare, they are Maxwell-Boltzmann ordinary particles are spinless. These are integral spins. Bose-Einstein and fermions have half integral spins. Wave functions, no wave function for Maxwell-Boltzmann. Symmetric bosons are symmetric and fermions are antisymmetric. And no upper limit of the particle. Here, no upper limit in the quantum state, but in Fermi-Dirac, there is an upper limit because of the Paul-Schild principle. And distribution function is e to the power minus epsilon by k beta t. This is 1 by e to the power alpha e to the power this minus 1, and when it is plus 1, this is Fermi-Dirac distribution function. Now, the next one is applications of Fermi-Bose statistics, where we can apply Fermi-Bose statistics. We can apply these statistics in various ways, various fields. These fermions and bosons in quantum mechanics are most used factors which explains the applications. The first application is the derivation of Planck's radiation law. Bose-Einstein theory is capable to this one Richardson's Dushman equation in thermodynamic physics can be derived. Look at this one. We know this expression for Fermi-Bose statistics. The number of particles n is Cv k beta t to the power 3 by 2 x to the power half dx by t. If you plot the graphs, you find this one. This is a mean occupation number for strongly degenerate Fermi gas at two different temperatures. This is the width of the tail of the Fermi distribution. This is width of the tail, k beta t. Here k beta t is small, here k beta t is large. So because x0 is mu by k beta t, this when simplified, this gives rise to your chemical potential and value of Fermi temperature. That is chemical potential at T is epsilon F Fermi energy into 1 minus pi square by 12 T minus Tf whole square plus pi 4 by 80 T by Tf to the power 4. So when you move in this manner, you will find that there are large number of applications. One is your electronic heat capacity. You can apply these two statistics to calculate electronic heat capacity, where in a mathematical function you can say total energy is the total internal energy is the total number of quantum states into epsilon is the energy of each quantum states. So you can find the total energy by using Sommerfeld's lemma, which is integration 0 to infinity f of x minus x0 into x to the power s into dx is equal to x0 to the power s plus 1 by s plus 1. If you use this lemma, you can calculate the total energy. And this is classically, you have this total energy. If you plot a graph, this is the expression for total energy is 3 by 5 n epsilon f into 1 plus 5 pi square by 12 t by tf square minus pi 4 by 16. If you plot a graph, you will find U versus T graph. This is for ideal Fermi gas and this is for ideal classical gas. You see the internal energy of strong degenerate Fermi gas as a function of temperature, that is at 0 point energy. This is at 0 point energy for Fermi gas. This is for ideal gas. You find how they in classical and quantum gases they vary. And the thermal capacity expression you can find from Cv is del E by del T, the expression will be pi square by 2 n epsilon f T by Tf square, which gives pi square by 2 n k beta T by Tf into T. Similarly, you have large other applications to calculate the entropy of this function. That is, the entropy is integration 0 to t Cv by T into dt, and you can also apply to thermionic emission. And you can also derive the Richardson's equation, Richardson-Dushman equation, that is thermionic current for unit area. This is Richardson's equation, that is 2E by HQ integration dP LZ, Z axis, integration minus infinity to infinity, dP Ly axis. This is number of particles in Fermi-Dirac statistics. Integration range is root over 2mEc to infinity. Vx dp Lx. So thermionic emission, Richardson's T square formula and T half formula we have read in our +2 stage, that is J is equal to some constant A T square e to the power minus beta by T. If you simplify this, you can find this Richardson's equation, how the Fermi gases are capable under condition applications of heat, they are capable to generate the electrons. Hence, this is one application. Another one is magnetic behavior of ideal gas. The gases shows the magnetic behavior. Under equilibrium stage, the non-interacting fermions under external magnetic field, we can calculate the net magnetic moment, and we can calculate the susceptibility also. So the Fermi gases, ideal Fermi gases shows the magnetic behavior. Therefore, we calculate the Pauli paramagnetism if we consider the energy of the particle epsilon is p square by 2m and some magnetic term mu star beta. Mu star is your intrinsic magnetic moment. Then mu star is maybe anti-parallel with magnetic field, or mu star is parallel with magnetic field. In both the cases, you can calculate the value for paramagnetism, and the Pauli spleen gives this beautiful picture that for at 0 degree Kelvin, this is magnetic moment which is parallel to magnetic axis, magnetic moment which is anti-parallel. If it is parallel, this is 1 by 2 f of E minus mu b, and this is E minus mu b. This is for anti-parallel, this graph, this is n plus parallel, this is n minus. So this clearly indicates that the magnetic moments are related with the Fermi gas as well as the Fermi energy state. Within the Fermi energy they are occupied. There are so many applications of these fermions and bosons. Similarly, you have applications of strongly degenerate boson gas. Like fermion gas, we have strongly degenerate boson gas, which gives you a superfluidity state. One application is superfluidity state and Bose-Einstein condensation. Bose-Einstein condensation leads to your superfluidity state. And what is your superfluidity state? In a superfluidity state, you come across the particles are very, the fundamental importance of Bose-Einstein condensation is superfluidity. It is the property of liquid helium at very low temperature that enables it to flow without friction. So at a superfluid state without any friction, the particles are capable to move, and this Bose-Einstein condensation, the number of particles in the ground state is like this. Mg is total number of particles minus 2.612 V 2 pi mk beta t by h square to the power 3 by 2. So this equation indicates the bosons gradually accumulate lower energy levels. This is called lower energy levels, and a large number of occupy ground state. This is called Bose-Einstein condensation. Unlike condensation, this is a vapor. Vapor is converted to liquid, or no special separation in two phases are there. with different properties. So this is called Bose-Einstein condensation, and XT explains the superfluidity state. So we discussed here mostly the fermions and bosons as regards to the statistical mechanics is concerned. Any questions? Okay, thank you for
Hello,
your
sir.
questions. Let us.
Hello. Hello. Hello, sir. Hello.
Mm.